So we started our discussion on oscillator last day. We have two types of RC oscillator. One was RC phase shift oscillator, and second one was Wien Bridge oscillator. The basic idea behind the oscillation is that, let me once again recapitulate what we have discussed last day. Basically, we have once again considering we are considering this particular feedback network consisting of the feed block and the back network. For a conventional feedback, as you know, feed forward signal is propagated in that particular fashion, left to right. Portion of if I consider this is my output, final output, a portion of the output is fed back through this back network. And what happens if I consider a negative kind of, so that is nothing but the sampling operation that we have done, and you know that there are different types of sampling. There are different types of sampling, voltage sampling, and then whatever be the mode of sampling, a portion of the output is fed back to the back network. Then it is processed, right? And then it is mixed at the input side. While mixing, you can have, so what we have done over there, so for a traditional case, what we have done, we have used some mixing stage over there, something like this. All them written like a summation sign, but as you understand that this is, if it is plus, this can be either plus or minus. Summation, so summation or subtraction, I mean the notionality is the same, plus and minus. So if it is plus minus something like that, it is known as a negative kind of feedback. That means input, if I call this input as, say, let it be, say, this is IP, that is input, and that was the final output. And if this is the effective input, if I call it like S epsilon, and if this is the feedback part, SF, I can call it like SI. This is S. So you know that this S of F is nothing but a function of S of O, and this S of epsilon, this is equal to, I can write it like plus minus S of F. Plus minus S of F. So here mixing part, so these two signals SI and SF, they can be added in the same phase or they can be added in the phase. So that's why this summation sign. Now if it is plus plus, known as a positive kind of feedback, and if it is plus minus, it's a negative feedback. And in the last unit you have studied the negative. Every time you have seen that if my input is something like this, if the input is over here, the input is like this, actual input, and then the input getting from the back network would be something like that. Reduced, but the phase is opposite. So whenever it goes positive, this goes negative. Right, and ultimately the system becomes stable. Okay, that is the notion of the negative feedback. Now what we have studied, and in that particular case we have also discussed that this particular network, this B network, consists of only resistances. We have only resistors, more than one resistance, like this. So that was the basic idea behind the feedback network or feedback topology. Now we have basically incorporated that network with some minor modifications. Some modification lies in the form that now this time this back network, it doesn't involve only resistors. This time some frequency selective elements as well. So last day we have seen that apart from resistors we can also include some capacitors over there. So that output from this back network, this SF, no longer independent of frequency. It's a function of frequency. Right? It's a function of frequency because it involves frequency selective elements. Lastly, we have seen that, okay, apart from resistors, we can also include some capacitors. That is the first change with respect to the traditional feedback topology, feedback network. And the second part is that, obviously, for the oscillator, you don't have any explicit input. You don't have any explicit input. So that SI was absent completely. So there is no SI. And this feedback signal is actually provided at the input of this feed network. Right? That means this S epsilon and SF, they are same because SI is absent. And when the signal is traversing in this path, from here to here and from here to here, total loop gain is equal to unity, and there is no phase reversal. There is no phase reversal. That means the phase of the input at any particular instant, suppose the phase, the input is positive. So for example, now let me modify this one in connection to considered for oscillator circuit. It was something like this. For oscillator circuit, this is modified like this. And now observe, suppose this is in the first instant the input, the input to the feed network looks like this. In the second instant, the input is this. Third instant, input is this. That means what? When a signal is traversing through this path, it will experience some gain as well as it will experience some phase difference through this A network. Right. So over here, this output, if this is your input, what is the output? There is nothing but this input multiplied with AS, where AS is the gain. And as you understand, since it is AS, that means it's a function of frequency as well. So it involves some gain and some phase difference as well. And whenever the same signal is also traversing through this B network, then obviously over here, what will be the output? This input multiplied with AS multiplied with BS. And that is the total loop gain. AS times BS. AS BS. And in order to establish, or in order to obtain some sustained kind of output over here, we have to ensure that this loop gain, what we call last day, we call this loop gain as LS, right? This loop gain was written like AS times BS. The total loop gain, mod of LS. Mod of S is equal to unity, right? And the corresponding phase difference from here, if I consider from here to here and here to here, coming back over a point, so the total phase difference is equal to 0 degree or 360 degree phase difference, and that condition is known as Barkhausen condition or Barkhausen criteria for oscillation. For sustained oscillation, you have to expect that whenever the signal is traversing through this feed network and the back network, the total loop gain is equal to unity in magnitude, and the phase difference is equal to 0 degree or 360 degree. So there is a kind of regenerative kind of feedback. You don't expect some negative feedback over there. Had this been a negative feedback, then your output cannot be a sustained one. It will be damped output. Right? And the gain factor, that is ASBS, it cannot be greater than 1. Because if it is greater than 1, then over here you can have this output is also, it's not, magnitude will be increasing, something like that. So what you expect? You expect that over here the output, you should expect that over here, this output should be something like this. Sustained, this is known as a sustained oscillation. Over time, so this is the same axis, over time, this is your output. That is expected. Some constant frequency and constant amplitude. Now, suppose output looks something like that. Say for example, it's a damp oscillation. That means this mod AS base is equal to 1 and angle AS base is equal to 0 degree. That's satisfied, damp oscillation. Or this is not also expected. This is not also expected. That means unstable system. Unstable. So none of this, these two are not desired. This one is desired. That means a sustained oscillation. And whenever this condition, that Barkhausen condition, Barkhausen criteria is established, is satisfied only for a single frequency, then this sustained oscillation is possible to have only for a single frequency. As I told you last day, typically whenever you just power on the circuit, so the initial input is coming from the external environment, the external noise. Typically it's a wideband noise. It can have the frequency range from a few hertz to few, for example, a few kilohertz, or tens of kilohertz, hundreds of kilohertz. And only for a given R, last we have discussed this RC oscillator, for a given R and C value, this sustained oscillation takes place only for a single frequency. And we have calculated those two frequency values, one for this oscillator and another for Wien Bridge oscillator. For phase shift oscillator, the naught was coming to be 1 by 2 pi root 6 times RC. For the Wien Bridge oscillator, as you can see over here, this oscillation frequency, hertz frequency is given by 1 by twice pi RC. So for given R and given C, this oscillation frequency is a constant one, is a fixed one. And in the universe, sinusoidal signal is the only signal available in the universe which consists of a single frequency. Right? It is the only signal available in the universe which consists of a single frequency, only one. That's why it is known as the monotone signal. Mono means one, single, and tone means the frequency. Right? So monotone signal, sinusoidal signal is known as a monotone signal because it consists of a single frequency. Now, since the Barkhausen condition is satisfied only for a single frequency, that's why it is known as the sinusoidal signal oscillator. That means it can generate the sinusoidal signal. Monotone oscillator you can call this Wien Bridge oscillator or the phase shift oscillator. But for a given value of R and C, typically these oscillators, these RC we discussed last day, these oscillators meant for the audio frequency generation. In the range of, say, do you have any idea what is the range of audio frequency? 20 kilohertz. Audio frequency? Yeah, it's in the range of kilohertz. 20 kilohertz to megahertz. What is audio? For human being, what is audible range? For human being, it is 20 hertz to 20 kilohertz is the audible range, right? So whenever I'm speaking something. Right now I'm speaking something. If you just record voice, right? If you record this voice and if you analyze this signal, this time domain signal and the frequency, then you'll see that the highest frequency produced by me, by my vocal cord, is restricted within, say, 3 to 4 kilohertz. 4 kilohertz maximum. I cannot generate anything beyond. Now, there are some singers who can produce up to, say, 8 kilohertz, 10 kilohertz. It's possible for the singers, not for typical human being. And for which, in the range of 15 kilohertz, 18 kilohertz, 12 kilohertz, that is possible to be generated. There is an experiment. In the next semester, the computing software laboratory, there is an experiment where we generate the frequency, the sinusoidal signal of varying frequency, starting from few hertz or tens of hertz to some tens of kilohertz. And you will just perceive what is the essence of that particular signal generation. So initially, whenever the frequency is in the range of say hertz or hundreds of hertz or say a few kilohertz, 1 kilohertz, 2 kilohertz, then you can listen to it properly. And as the frequency increases from 2 to 3, 3 to 4, 4 to 5, 10, 12, 15 like this, then the signal is becoming much more sharper, right? And a point will come when it is beyond some level, and obviously it depends upon the person who is listening to it. Somebody can perceive up to 12 kilohertz. Typically, 20 kilohertz is known as the audible range, that is the maximum. But for any human being, it is not possible to perceive up to 20 kilohertz or right at 20 kilohertz. It's not just possible. We cannot perceive any signal frequency which is what larger than 15 kilohertz or say 16 kilohertz. Beyond 15 and 16 you cannot hear properly. So there is an experiment in the next semester in the computing software laboratory where this signal will be generated, produced through software by writing codes. You have to generate that signal and then you have to listen to it. And depending on for every group, they will write the same code. And when the program is run, then you have to listen to this voice, to this particular music. It's not music rather, that particular signal, monotone signal, and you have to mark that point up to which you can hear. That depends from group it may vary. Somebody may claim that up to 10 kilohertz, somebody may claim that up to 12 kilohertz. So you cannot perceive beyond 20 kilohertz. That is the maximum range for human being. But for other creatures, as you know, for the dog especially, this audible range is little bit large. Even they can hear before 20 hertz. They can hear. We cannot hear if your input is like if your input signal frequency is 20 or 50 hertz, then we can hear only 50 hertz onwards. The dog especially they can listen to the frequency which is less than this 20 hertz, right? So anyway, so that is the audible range. If you know that is audible range, audio frequency range in the range of few kilohertz, 5 kilohertz, 8 kilohertz, 10 kilohertz, that is audible range. And for the generation of in the audible range, this RC phase shift oscillator and RC this Wien Bridge oscillator, this is used. But sometimes your requirement is that you need to generate some signal frequency, some signal at pretty large frequency in the range of megahertz, not only in the range of kilohertz. You have to generate some signal frequency in the range of megahertz. What is the use? Right at this moment, you will not be able to understand what is the use. But hopefully, in the next semester, there is another subject which is the signal transmission and communication system. There is a subject called signal transmission communication system. They will see that they will study over there the different types of the transmitters and the receiver sections, like radio receivers, the television receivers. Over there, you have to capture signals you have to capture signals in the range of megahertz, right? In the range of megahertz. The frequency range of our this FM communication. I'm not telling AM because AM is pretty old. You are not, hopefully, you are not aware of what is AM radio, amplified radio. But still, I have some idea of what is FM radio, right? FM, I think you have heard of FM, but not AM, right? Amplitude modulation, you have not heard. But frequency modulation, the term FM you have heard, right? Frequency modulation. So do you have any idea what is the range of frequency over which this FM is operated?
93.5.
What is that? 93.5 means what? That's a channel frequency. What is that? 93.5 hertz?
Gigahertz.
Kilohertz, megahertz, gigahertz, terahertz. What is that? You know the number 93.5 and whatever it may be. 100.2 like this. 88 point something. So typically it's megahertz in the range of megahertz. Right. In India, it is from 88 megahertz to 108 megahertz. That is the range. 88 to 108 range. Right. 88 to 108, 20 megahertz. So suppose you have to generate some signal at that particular frequency in the range of megahertz. In that case, this RC oscillator will not work. Why? Because at very high frequency, if you have studied that, okay, there are 3 different RC stages. Last week we have explained that there are 3 different RC stages, and they have to be identical in nature. You have RC, 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 right? And these 3 stages will be identical. So that I have arrived at that particular expression that this omega naught is equal to 1 by 2 pi root 6 RC. Now at very high frequency, what happens? These resistors are not alone register. Apart from that, they can also exhibit some behavior of an inductor in series and capacitor in parallel. Some parasitic effect you can expect at very high frequency. So therefore, for very high frequency, if you would like to generate some signal of a given frequency, and to ensure that this is a stable frequency generation, then people have opted for the LC oscillator, which involves inductor and. So let me just show you a typical generic architecture for an LC oscillator. How does it look like? a generic LC oscillator. As I told you last day, so this oscillator circuit involves the amplifier and it involves a back network, a feed network and a back network. So typically this is your feed network, amplifier represented by some black box, right? Typical amplifier, and then in the back network what we have, in the back network now you have three such reactive elements. As you understand, if I have an inductor, if I have a capacitor, typically for inductor whose inductance is equal to L, impedance is given by j omega L, and for capacitor whose this value is equal to C, I have not marked over there anyway. If this is C, then 1 by j omega C, right? So therefore they can be represented in the form of j into x. Because 1 by j omega c can also be written as minus j times 1 by omega c, right? So therefore, this inductor, both these inductors and capacitors are represented in the form of j times x, where x is a real number, j times x. So therefore, here we find that for typical LC oscillator, used three different such reactive elements. This is jx1, this is jx3, this is jx2, and connection diagram. That is the connection diagram. This is the output of the amplifier, and then this is your back network, and a portion of the output is fed back to the input, and there is no such explicit input present, just like our previously discussed RC oscillators. Okay. So therefore, obviously for this one, as you understand, if this current is equal to, if this total current is equal to I, and suppose there is a branching of current I1 through this path and I2 to that branch, then what will be your I1 value? How can you represent I1? How is related in terms of V0, where V0 is your output voltage? I mean, how I1 and I2 is related? This is V0, this is V0, this voltage is V0, this total current is I1 plus I2, the current I2 is flowing through this branch and I1 is flowing through this branch, right? So what is the relation between I2 and V0? I2 multiplied with Jx2 is equal to your V0, right? And what about your I1?
I1 is Jx3 parallel this.
What is I1? From here to here, the voltage difference? V0. Right. Here to here, what is the voltage? That is V0. What is the total impedance? J into x1 plus x3. So V0 upon this. As simple as that. Now, once again, let's now observe output side of the amplifier. What do you have? The output side. The output side, you have some. You already know that there is a GM pi R naught parallel, right? GM pi, a voltage dependent current source in parallel with some R naught. You can also represent using source transformation. You can also represent this as GM pi parallel. I mean, what you already know this one, the output side of a transistor, GM pi and parallel R naught, right? You already know this one. Now using source transformation, what you can do? This is nothing but this is R naught. So this is nothing but a voltage source in series with R naught. Right? So we'd like to observe this one at the output side of this amplifier. So you have some AVVN, which is known as the circuit voltage, where V is input to the amplifier and AV is the gain of the amplifier. So open circuit voltage AVVN and R naught is in series. Okay. So we would like to observe only the output part of the amplifier. This is their AVV and this is the output voltage, that is V0. What you have? You have this one, this JX2, one reactance over there, and this combination JX1, JX3, and this is the feedback voltage. Okay. Now let's do some mathematics, some cases here. What is this I? How can we represent I? This I is nothing but this voltage minus this voltage divided by this R0. Right, AVVN minus V0 upon R0, and that is equal to the summation of these two currents, where the current through this branch is equal to I2 hopefully, and the current through this branch is equal to I1. So what is that current? As you know, this current is nothing but V0 upon JX2. What is that current? That current is nothing but V0 upon J into X1 plus X3. So if you just simplify this one, then ultimately what you are getting is AVVN is equal to V0 multiplied with this factor. Now this final expression is of our interest. What is your AVV in? What is your AVV in? That is the open circuit voltage generated by the amplifier itself. And what is your V0? V0 is equal to your output voltage. Right? Then what is the feedback voltage that has been generated by this network? This feedback voltage. What is that? This voltage across this JX1. What is that? This is nothing but this is the current that is flowing through this multiplied with this JX1. Right? So what is that? Nothing but V0 upon X1 plus X3 multiplied with X1. Okay. Clear? If you just substitute those values, then ultimately this VF is coming out to be JV times V in X1 X2 upon JX2 into X1 plus X3 plus R0 into X1 plus X2 plus X3. Then what is the loop gain? What is the loop gain? Initially you have started with, so let me once again go back over here. This input was, initially this input was V in. Initially that input was V in. Then through this amplification operation, you have generated some AV times V in. Right? AV in is nothing but your open circuit voltage. Now whenever you connect some load, that becomes V0. V0 is the output voltage, and a portion of the output voltage is being fed at the in the form of VF. So initially in the first iteration, that input was V in. Then through this amplification and through this feedback, through this back network, once again the voltage that is being fed is equal to VF. What is your loop gain? Loop gain is nothing but this VF upon V in. Again, and you have to expect, or you have to establish that this VF of a particular thing must obey the Barkhausen condition. That means whenever the right input over here is equal to V in, and whenever this input is traversing through this, and whenever it is once again coming back over here, you'll be having the same signal. So if your initial input is something like that, then after one iteration it will be something like this. The same thing, no change. No phase reversal, no phase, no gain, no attenuation. So this VF upon Vn must be equal to unity. Okay, so we have already got what is VF upon Vn, that is equal to, as you can understand over here, this is nothing but this one, J times AV times X1 times X2 upon Jx2 into X1 plus X3 plus R0 into X1 plus X2 plus X3. You have to ensure that this factor, this loop gain, this one, VF upon V in this entire thing, this should be unity. Mod of this LS should be equal to 1, and angle of this LS must be equal to 0 degree. Mod of LS is equal to 1, and angle of LS is equal to 0 degree. Now what you find here, in the numerator you have some JAVX on X2. In the denominator you have something like in the form of A plus JB, in the form of A plus JB, a complex number. The numerator you have imaginary number, the denominator you have some complex number. Now if you would like to make it a pure real term, what is the condition that I have to ensure? That means this entire thing, this R0 X1 plus X2 plus X3 has to be 0. R0 is non-zero, so therefore X1 plus X2 plus X3 is equal to 0. That is the condition for any generic oscillator. For any generically C oscillator, x1 plus x2 plus x3 must be equal to 0. Okay. And then x1 plus x2 plus x3 is equal to 0. Then what will be your LS? You can simply plug in those values. Then ultimately you are getting to be minus of x1 by x2 times AV. Minus of x1 plus x2 times AV. That is the loop gain. Now how can you ensure that x1, x2, x1 plus x2 plus x3 is equal to 0? Condition is that to satisfy the Barkhausen condition, this x1 plus x2 plus x3 is equal to 0. Right? This is quite obvious. x1 plus x2 plus x3 is equal to 0. Now, had this been the case, then what is your V upon V? This is becoming 0. So you have J gets cancelled. You have x2 gets cancelled. So you have what is x1 plus x3? That is minus x2. Right? Minus here. So minus x1 by x2 times AV. That is the loop gain. Minus x1 by x2 times AV. Once again, you have to ensure that this loop gain is a real number. Loop gain is a real number. And you are getting it as minus x1 by x2 times AV. So how can you expect that it's a real number? AV is a real number. So therefore, x1 and x2, they must be of the same type. Either both of them are inductor or both of them are capacitor. If both of them are inductor, then omega L1 by omega L2. And if they are capacitor, then 1 by omega C1 by 1 by omega C2. So this x1 by x2 will be independent. Can you get the point? So either x1 and x2, both of them are inductor, or both x1 and x2 they are capacitor. So that this x1 by x2, this particular ratio is not a function of frequency. Frequency, then obviously it will be having the corresponding phase shift that you don't want. Okay. So if both x1 and x2 they are, so x1 plus x2 plus x3 is equal to 0, and so therefore you can get x1 plus x2 is equal to minus x3. So therefore the condition is that both x1 and x2 they are of same type. Now if both of them are inductor, x1 and x2 they are inductor and x3 is a capacitor, then it is known as a Hartley oscillator. It's a Hartley oscillator, right? And for Hartley oscillator, I can write x1 as omega L1, x2 as omega L2 like this, and x3 is by minus 1 omega C3, and then what you get, this oscillation frequency as 1 square root of L effective into C3. What is L effective? This is nothing but the summation of L1 plus L2, L1 plus L2. Okay, that is the basic notion behind the Hartley oscillation, Hartley oscillator. And both x1 and x2 they are capacitor and x3 is an inductor. Then it is known as a Colpitts oscillator. Okay, Colpitts oscillator, in which case x1 is equal to minus 1 by omega C1, x2 is equal to minus C2, x3 is equal to omega L3, and then if you just satisfy the condition that x1 plus x2 x3 is equal to 0, then ultimately this oscillation frequency is coming out to be 1 by square root of L3 times C effective, where C effective is nothing but the C1 C2 by C1 plus C2. Okay, so for generic oscillation, the condition which has to be satisfied is that x1 plus x2 plus x3 is equal to 0, right? And x1 and x2 they are inductor, x3 is a capacitor, then it's a Hartley oscillator. And if both x1 and x2 they are capacitor and x3 is an inductor, then it is known as a Colpitts oscillator. Now let's go for the implementation. So there, this particular representation, we have just considered some generic block diagram. Then we go for some specific design for Hartley and then Colpitts oscillator. What is that oscillator? What is that oscillator? Is it Hartley or Colpitts?
Hartley.
First of all, this is your amplifier, voltmeter, common emitter with bypass, emitter resistance bypassed, right? And then what you have? Then what you have after this? Then what we have after this? This L1, L2 and C3. Yes, why coming to that? This L1, L2, C3. This one was your JX2, right? This is your JX3. This is our JX1, and from this X1, X3 common point, the feedback is provided at the input of the and this base over there. This is nothing but your JX2. This is nothing but your X3. This is nothing but your JX1. That is in, right? Now you may argue, you may ask why this C dash is present. Why it is needed? Any dash is there? That's a hard ground. That's a hard ground. This C dash is present over there. So this C dash will not take part. This C dash will not take part in the oscillation. In the oscillation, for the oscillation purpose, this L1, L2 and C3, they are responsible. L1, L2, C3. That means this JX2, JX3, they are responsible. But the question is that why this C dash is present over there? You will look very minutely. Here, this is your output for the amplifier obtained from the collector end, and this is the input obtained at the base end. Now this collector and base, they are connected by means of two inductors, L1 and L2. This is a collector terminal. Through L2, this base is connected. Okay. And apart from that, you have this particular C3. So what is the need of having this test over there? What is the need? Collector to base. This connection is made L2, L1 over here, and then you have this C3. So C3 also you have this connection. The question is that why should you go for a test? Which one? What is the use of a capacitor? What is the use of a capacitor? What is the use of a capacitor? We can also modify this one. I don't know whether it is there in the next part or not. No, it is not. Anyway, this is not. This is not there. Sometimes you don't require this R1 or 2 also. Some require R1 or 2 also. Why this biasing can be done directly? Right? This biasing can be done directly. DC wise they are shorted to some extent. DC wise they are shorted now. Whenever you go for a DC operation, this capacitor will act open circuit. So this will not work. This capacitor C3. This will not work. C3 will not work. But if you consider from here to here, during the DC operation, this L2 and L1, they will act as omega L1, omega L2, omega equal to 0. So DC wise they are shorted. DC wise they are collector and base. DC wise they are shorted. So I have to go see that. Think about it. Why it is required. Let's see this one. Colpitts oscillator. These are two capacitors, one inductor. You require C1 in the form of a capacitor and L3 in the form of an inductor. Additionally, there you have connected and C dash over there. What is the need? Remember that C dash doesn't take part in the oscillation operation. You know, to prevent that, okay, this collector and base, they are not wise, they are at the same level. And to prevent that, the C dash is present. C1, C2, C3, C1, C2, L3, they will take part in the oscillation, in the design of the oscillator circuit. C1, C2, and L3. But C dash value is different. Why C dash is there? You have to ensure that this part, this voltage over here, and this voltage over here, they are DC wise at different level. DC wise, they are at different level.
So it creates a potential. Potential.
It's not potential drop. DC are at the different potential. This collector and the base. You have to ensure that you have used this C dash so that DC are not at the same level. That means if you have some C dash over there, so obviously this is not. So this part is not connected to this part. Open. Capacitor is open to any DC operation, to any DC signal, and inductor will act as a short. Right. So sometimes if they are like DC wise, if they are connected like this, even for the last circuit, if they are DC wise connected, then you don't require an additional this R1 R2 for biasing. You get the biasing directly. Okay. So that's all about your Hartley and the Colpitts oscillator. So these are the individual description using the BJT model, and to obtain this one, this Colpitts and Hartley from the generic structure. First of all, you have to derive that expression, which is to be satisfied. That is x1 plus x2 plus is equal to 0, and then for some specific applications, if x2 is an inductor, x3 is a capacitor, then you go for Hartley, and if L1 and that means 2 are inductors, L1 and L2, C3 is a capacitor, it's a Hartley oscillator, and for Colpitts, this x1 and x2, that means C1 and C2, they are capacitors, and L3 is an inductor. Right, and you have to justify the use of these additional capacitors over there. Why this additional apart from this C1, L2, C1, C2, L3, or L1, L2, C3, why the additional capacitor C dash is present? What is the use of that particular capacitor? So to answer this question, you have to understand what is the use of capacitor in the DC operation. What is the use of the capacitor in the DC operation? And accordingly, you have to design the circuit. Okay. So with this, we have come to the end of these LC oscillators and the oscillator circuit as a whole.